And welcome back once again to the History of Mathematics. We are going to continue our work through Chapter 14 of our text, Stuart Hollingdale's Makers of Mathematics. And we're discussing the work and contributions of Carl Friedrich Gauss. As we noted in the last video, he is considered by many to be the most prominent mathematician of all time because of his contributions to diverse fields in the discipline. And one of those contributions is a proof of the fundamental theorem of algebra. Gauss was actually awarded his doctoral degree for this proof. So we're not going to go over the entire theorem. We're going to go over an important supporting idea. So let's switch over to the document camera and work on that. So we actually have two different ways to state the fundamental theorem of algebra. First is that every non-constant single variable polynomial has at least one complex root. And there's a second version. You can actually prove it's equivalent to this. The second version says every non-zero degree n polynomial has exactly n complex roots if we count with multiplicity. So I wanted to talk about the idea of roots of unity. And roots of unity are about solutions to polynomials of the form z power n minus 1 equals 0. Okay, so we're talking about complex numbers that we can raise to the nth power and get 1 to make this equation work. Now, according to version 2 of the fundamental theorem of algebra, there should be exactly n complex numbers that will do this if we count with multiplicity. And in this particular case, it's actually going to turn out there are n distinct complex numbers that make this equation true. So let's go ahead and look at a concrete example here. Give myself a little space here. Okay, so we're going to go ahead and find the third roots of unity. Okay, in other words, we're going to solve the equation z power 3 minus 1 equals 0. Now, we can actually get this problem solved with fairly elementary tools. This polynomial factors as the difference of cubes, and it factors into z minus 1 times z squared plus z plus 1. Okay, now of course, I'm sure you remember from your algebra class that finding the factors is equivalent to finding the zeros. So one of the roots of unity is z equals 1. That's a complex number that has this property. The other two can be found by taking this other factor and solving the equation that we get by setting that factor equal to 0. Now, of course, we started with a third degree, and we factored it into a linear times a quadratic, so now we're working with a simpler problem, so we can solve that with the quadratic formula. Okay, so scoops this down here like such. Okay, so of course we know it's x equals negative b plus or minus square root b squared minus 4ac whole thing over 2a. And it turns out that a, b, and c are all equal to positive 1. So this would be negative 1 plus or minus square root. Okay, now b squared would be 1, and minus 4ac would be minus 4. So this is minus 3 under the square root sign there, whole thing over 2 times 1. Okay, so third roots of unity are 1, negative half plus root 3 over 2i, and negative half minus root 3 over 2i. Okay, of course, when we take a square root of a negative number, that takes us into the complex number system. Okay, so these are the three distinct complex numbers that you can cube and get 1 as the result. All right, now this case is almost a little too simple, because when you factor, you get a quadratic here, and you can solve that with the quadratic formula. You might not be able to do that all the time, so we're going to take a look at this from a geometric point of view and see how we can get the nth roots of unity in other cases. Okay, so what I've got here is a kind of a crude little drawing. Let me improve on this just a little bit. I see where I messed up. Get a little better circle going here. Okay, so I've got a drawing of the unit circle in the complex plane. Okay, this is the real axis, and that's the imaginary axis. Now, when we're talking about the third roots of unity, okay, 1 is always going to be a root of unity no matter what degree you're talking about. But what I want here are, I want 3 points on this unit circle evenly spaced on the unit circle, and one of them has to be here. Okay, so, well, the unit circle would be 360 degrees, or 2 pi radians. So if I want 3 equally spaced points on the unit circle, what I would do is I would take 2 pi, divide by 3. And then I would have double that. And I guess you could go full on. Three pi divided by 3, but that just gets us right back here. Okay, now 2 pi over 3, that's somewhere over here. And the other root of unity, it turns out, is going to be somewhere over here at 4 pi divided by 3. Okay, now every point on this unit circle, if you remember Euler's identity, every point on this unit circle has coordinates cosine theta plus, clean this up a little bit, cosine theta plus I sine theta for different values of theta. And if we're talking about third roots of unity, these are the values of theta that we should use. Okay, so if I did cosine 2 pi over 3 plus I sine 2 pi over 3, well, these are some special angles, right? We know the values of the trig functions for these angles. Okay, and it turns out that this is -1/2, and sine of 2 pi over 3 is radical 3 over 2. Okay, so this is -1/2 plus radical 3 over 2i. And cosine 4 pi over 3 plus I sine 4 pi over 3. You remember your trigonometry here. This is -1/2 minus root 3 over 2i. And if I did cosine 6 pi over 3 plus I sine 6 pi over 3, well, this is sine of 2 pi, that's 0. This is cosine of 2 pi, and that's 1. So we get 1. Okay, so we get the three roots of unity this way. Now, we might need to do this type of stuff with higher degree polynomials. So if I wanted to find the fourth roots of unity, for example, I would take 2 pi over 4, 2 times 2 pi over 4, 3 times 2 pi over 4, and finally 4 times 2 pi over 4. And that would get me the fourth roots of unity after I plug those values into this expression right here for theta. So the actual proof of the fundamental theorem of algebra, even the one that Gauss did, is a little beyond the scope of our course right now. But I did want to give you a flavor of kind of working with complex numbers and dealing with finding n roots to an n degree polynomial. So these are the roots of unity. So our next video, which we will link to right down here, will actually deal with the work of Sir William Rowan Hamilton, who was able to kind of extend the complex number system. He's famous for creating something called quaternions. So that'll be the topic in our next post.